Dear student friends, welcome to the class of BSc first year mathematics. And today we are going to start the paper of geometry in the second semester. So BSc first mathematics, and we are going to study paper number is MAT 202 geometry. In this paper we shall study the topics. First is the plane, the second is the right line, third is sphere, next we will study cones and cylinders, and last one is conicoids. So first chapter is the plane. In this chapter, we will study equation of plane and different forms of equation of a plane, then angle between planes and distance between point and plane, etc. Now today we will study the equation of plane, and for studying equation of plane we will first write general equation of first degree. General equation of first degree. So a general equation of first degree or of the first degree in variables in x, y, z is of the form ax plus by plus cz plus d is equal to 0, where the condition is where abc are real numbers which are not all 0. That means at least one of them is non-zero. See, this is the equation. Ax plus by plus cz plus d is equal to 0. ABC are real numbers or constants, and the condition is not all are 0. If what happens if all are 0? If A is 0, B is 0 and C is also 0, then the equation will not exist. Then D is also 0. So nothing will exist, and therefore at least one of them is non-zero. So this condition is equivalent to. So the last condition, the condition ABC are not all 0 is equivalent to a square plus b square plus c square is not equal to 0. It is the same. If not all 0, then the sum of squares will not be 0. So this is necessary because to exist the equation, and thus this is the first degree, general equation of first degree in x, y, z. Now why it is the first degree is obvious, because degree of x, y and z, the maximum power is 1, and therefore it is the first degree equation. Now what we are going to show is this first degree equation, general equation of first degree in x, y, z, that is this equation, where a square plus b square plus c square is not equal to 0, represents a plane. And generally when we say a locus represents a plane, or what when this equation will represent a plane, a locus is said to be a plane if we consider any 2 points on the plane or on the locus. Suppose these 2 points are P and Q. Then the line joining PQ we will consider. Then every point on the line joining PQ must be on the locus. Then it will be a plane. That means if you consider any point, say here R, then R must be on the plane. Then it will be or the locus will be the plane. And see, this will not happen if you consider this type of surface. So this is not a plane, because if you consider the points P here and Q here, and if you join the line PQ, line joining PQ, then not all points, every point on this line is not on the locus. So this is a curved surface and this is not a plane. So the condition is, consider any 2 points on the locus, then every point on the line joining these 2 points must be on the plane. That is the condition for the plane, locus to be a plane. And now we will prove that this equation, first degree equation, represents a plane. That is our theorem first. Every equation of first degree represents a plane. Now we shall prove it. And as earlier we have seen, equation of first degree in xyz is of this form. So consider an equation of first degree. First degree in xyz as ax plus b into y plus c into z plus d is equal to 0, and we will suppose this as 1 such that condition is a square plus b square plus c square is not equal to 0, so that ABC will not be all 0, and thus this is the equation of first degree in xyz. Now what we want to show is this equation represents a plane, and as was seen earlier, we will consider the locus of this equation 1 and take any 2 points on this locus. Let we will take P x1 y1 z1 and Q x2 y2 z2 be any 2 points or arbitrary points. Arbitrary means chosen randomly. Any 2 points on the locus of equation 1. Locus means a surface or set of points satisfying the given geometrical condition. That means these are the 2 points on the locus surface represented by this equation 1. Now what we shall consider is the locus 1 will be a plane if every point on the line joining PQ is again on locus 1. The equation 1 will represent a plane if every point on the line PQ is on the locus y. So and now this is the condition for equation of plane. Take any 2 points, and then if you form the line joining the 2 points, then every point on the line must be on the locus. Now we will use this condition that P and Q are on the locus 1. Since P and Q on the locus 1, we have a point lies on the locus, means it must satisfy the equation of the locus. So this P and Q lies on this locus, the coordinates of P must satisfy equation 1, and that gives, see, these are the coordinates x1, y1, z1, and this satisfy the equation, means replace x, y, z by x1, y1, z1. So the equation becomes ax1 plus b into y1 plus c into z1 plus d is equal to 0. We denote this equation by this Roman digit 1. And second point is q, x2, y2, z2 is also on this locus, means the coordinates of the second point must also satisfy the equation, and the equation gives ax2 plus a into x2 plus b into y2 plus c into z2 plus d is equal to 0, and we number this as second. Now what we shall do is consider a number k, multiply the second equation by k and then add it in 1. Now multiply 2 by k, and we will choose k not equal to minus 1. Particularly, we will know why this is to be done. K is not equal to minus 1, and adding it to 1, we have, or we get. Now this is simple arithmetic calculation. You see, we have to multiply this by k and add this. So that will be ax1 plus ka x2. A is common, and we will have a in bracket x1 plus kx2, because we are multiplying this by k and then adding it to first equation. Now second term of the in the addition will be this b is common, and in bracket what remains, y1 plus, and this is multiplied by ky2. Next here c is common, and inside the bracket it will remain z1 plus k times z2, and plus d is there. I will write here plus d is common, and in bracket it is 1 here, and we are multiplying by k to the second equation, and this is equal to 0. So this is the operation we have done, multiplying second by k and adding it to first. Now we will divide by 1 plus k throughout. Dividing by 1 plus k, we get. Now here that is necessary that this must not be 0. We can't divide by 0, and this is not 0, means k must not be minus 1. So that's why we have written here k is not equal to minus 1, and therefore we can divide this equation by 1 plus k. So what we shall get is a in bracket. So this is to be divided by 1 plus k each. So x1 plus kx2 divided by 1 plus k. Second, plus b into bracket y1 plus k times y2 divided by 1 plus k, and plus c in bracket z1 plus k times z2 divided by 1 plus k, and plus d into 1 plus k divided by 1 plus k will remain only d is equal to 0. Now you see what this suggests. Now this shows that the point, this x1 plus kx2, we observe this equation 1. It is the equation 1 where x, y, z are replaced by these values, and thus this equation 1 is satisfied by the coordinates of a point whose x coordinate is this one, y coordinate is this one, and z coordinate is this. So thus this shows that the point See the point, the coordinates of the point will be, x coordinate is this bracket, x1 plus k times x2 divided by 1 plus k. Next is y1 plus k times y2 divided by 1 plus k. And lie on the locus 1, or locus represented by equation 1, because these coordinates satisfy this equation, a into this plus b into y coordinate plus c into z coordinate plus d is equal to 0. This is the part. So when a point's coordinates satisfy a certain equation, then we say the point lies on that surface. So this point lies on this surface. But now you see, what is this point? So this point means this is a point on the line joining P and Q. Why is it so? So P is this point having coordinate, and Q is another point we have considered. And I say this point, suppose if this is R, then it lies on this line. Because what are the coordinates? x1 plus k times x2. See, the coordinates of P are x1, y1, z1. And coordinates of Q are x2, y2, z2. And this point has these coordinates. So this is a point on the line. Because we know by section formula that this is the point which divides the segment joining P, Q in the ratio 1 to k. If the ratio is 1 to k, then we know this is or it will be reversed. So it is x1 plus k times x2. So interchanging this, you may consider x1 plus k times, or we know the bisection formula, it is mx1 plus nx2 divided by m plus n. And therefore if you consider this should be P and this should be Q point, and then the ratio is 1 to k. So 1x1 plus k x2 divided by 1 plus k. That gives exactly the coordinates of the point which divides the join of P and Q in the ratio 1 is to k. K is to 1. The ratio is k is to 1. So this point, this shows the point lie on the locus 1, since it is the point since, but this point lies on, or lie on the line, or simply we may say is on the line PQ, which divides segment PQ in the ratio 1 is to k, or k is to 1. The ratio is k is to 1. And thus we have shown that a point on the line PQ is again on the line PQ, lies on the line PQ. And this shows that every point joining, or every point on the line PQ lie on the locus. Every point on the line PQ lie on the locus, because P and Q are considered arbitrary, and therefore the locus 1 represents a plane, and hence, or thus, thus the locus 1 represents a plane. This is the condition required for plane. If you take 2 points, then the line joining these 2 points must have, every point on the line joining these 2 points must be on the same surface, then that is a plane. So this is what we have shown. So thus the locus 1 represents a plane. And that is, hence, what is locus 1? Locus 1 is the first degree. So therefore, every first degree equation in xyz represents a plane. Hence, every first degree equation in xyz represents a plane, and this completes the proof. So thus we have proved the theorem as every first degree equation represents a plane. We have considered first degree equation. We have taken 2 points P and Q, and then because the 2 points lie on the locus, this satisfies the equation of locus. We get this. We have done this operation and obtained this equation, and then this equation suggests that this point is on the locus 1. So that is means the point, every point on the line joining PQ is again on the locus 1, and that proves locus 1 represents a plane. Now we will consider the converse of this theorem. Converse of theorem 1. That means, see what is the meaning of converse. So first degree equation represent a plane. That is our first statement. Theorem 1. Converse of theorem 1. We know in logic what is a converse statement. If this is a logical statement, P implies Q, then its converse is Q implies P. So that is converse of this logical statement. If P, then Q. Here, if Q, then P. Now what we have proved earlier, first degree equation. First degree equation represents a plane. Then it implies plane. Now what will be a converse? Plane's equation, every equation must, equation of plane must be of first degree. That means we have to, if it is a plane, then its equation must be of first degree. So this is the converse that we have to prove. And the statement is, equation of every plane is of the first degree. First degree equation in xyz. So this is the converse result that we have to prove, and that means these imply each other. So if it is a first degree equation, then that if you combine these two, then they will imply each other, or they will be equivalent. First degree equation that represents plane, then its equation must be first degree equation. And now to prove this, we will consider a plane. So proof of this. Consider a plane. Any plane we will consider, and I will draw a figure like this. So suppose these are the axes, coordinate axes. Origin, and we shall show a plane like this. This is a plane. You have to imagine it is three-dimensional, and it is a plane sheet kept like this. And then we will draw perpendicular from origin to this plane. Suppose it is it may be say here it is perpendicular. Say OK is perpendicular on the plane. It's perpendicular, and suppose this point is K, and suppose P is any point on the plane, that is P, and we will join KP or PK. So this is the case we have considered. Let OK be the perpendicular from the origin O to the line, to the plane. Meeting K is the foot of perpendicular. Let K be the foot of perpendicular. Further, we will assume this OK distance is small p. Let OK is equal to small p. This is capital P point we are considering, and this is small p. Further, let P, capital P now, x, y, z be any point on the plane. One more thing we have to consider is let the direction cosines of OK be LMN. Let these are the direction cosines of OK. Now OK is perpendicular to the plane, means OK is perpendicular to PK. Now PK lies in the plane. See, this is to be imagined. P and K are on this plane, which we can imagine a sheet here kept like this. P and K are in the plane, and therefore PK is perpendicular to OK, because OK is perpendicular to the plane. So this is from the origin, and the plane is like this. It is perpendicular, and therefore PK line is perpendicular to OK. So this implies PK is perpendicular to OK, and therefore we will now consider the projection of OP on OK. This implies projection of OP on OK, and you may see this is OK itself, and which is small p. Now what is the situation is, see, this is projection of OP we are taking. This is O and this is P, and OP is perpendicular to OK. These points are, this is turned and P is taken here. So this is perpendicular. PK is perpendicular to OK. Projection of OP is same as OK. So it is a projected segment like this, and therefore it is OK. But the coordinates of O are 0, 0 origin, and P are x, y, z. But the projection of OP joining O origin 0, 0, 0 and P x, y, z on the line OK with direction cosines. The direction cosines of OK we have written as, here we see, direction cosines of OK are LMN. So with direction cosines, is, now this projection is this is the result from vectors or result from last year's geometry, and that is L into x minus 0. The direction cosines are LMN and the points are O and P. So L into x minus 0 plus M into y minus 0 plus N into z minus 0, or which is simply equal to Lx plus M into y plus N into z. So this is the projection of OP on OK. But what we have written here, the projection of OP on OK is, because it is perpendicular, it is simply OK, and that is P. So this projection is equal to P, but the projection is L into x plus M into y plus N into z, and we may suppose this as 1. Therefore from 1 we have, what is the projection? Projection is this one, Lx plus M into y plus N into z, and this is equal to P. It is equal to P. So thus this is the result we have obtained. And now you see P is a point. P is a point on the plane. Here we have written P is any point on the plane. Any is important, and that means every point on the plane satisfies this equation. So this shows that every point on the plane, this plane, every point P on this plane satisfies this equation, or you may suppose the equation second, satisfies equation 2. And therefore equation 2 is the equation of plane. And now you see what is the degree of this equation. It is the first degree. The powers of x, y, z or exponents of x, y, z are 1. Therefore it is first degree equation. And this shows that, or hence, every plane or equation of every plane, or the see, this shows that every point on the plane satisfies equation 2. Therefore equation 2 is the equation of plane. Equation 2 represents is the equation of the plane. But equation 2 is first degree equation. So therefore every equation of every plane is of first degree. Therefore equation of every plane is of the first degree. In x, y, z, and this proves the theorem. So thus this completes the converse part, and we have proved both these parts, and thus first degree equation and plane are equivalent. If the first degree equation in x, y, z, that represents a plane, and if it is a plane, then its equation is first degree equation in x, y, z. Now we write a note as first this equation Lx plus My plus Nz, the equation where what is Lmn, These are DCS, direction cosines of the perpendicular from origin to the plane. And what is P? P is the length of the perpendicular, is called the normal form. Normal form of equation of plane. And second thing we have studied earlier is the equation ax plus by plus cz, and that equation is known as general form. So the equation a into x plus b into y plus c into z plus d is equal to 0, where a square plus b square plus c square not equal to 0 is called the general form of equation of plane. So thus we have studied actually two equations. We have studied the things. Every equation of first degree represents a plane and vice versa. And there are two equations. Both are first degree equation. What is the change is here are ABC and here is LMN. So P is on the right side. If this is a particular form, then this form is called normal. Normal means perpendicular from origin to this plane. And this is general equation. Here A, B, C are the constants which are not all zero. And we have shown this also represents a plane. And this equation also represents a plane. These are the two forms of equation of plane that we have studied today. The remaining part we will continue in the next lecture. Thank you.